Welcome back to the Subscribe blog. Thank you for tuning in again. Today I'm going to talk about messaging. I'm going to talk about the brokered messaging capabilities that we have in Service Bus, both in the server and in the cloud. And this is going to be a fairly long talk because I want to have for you one place that you can go to and that you don't have to guess which feature sits where. So I'm going to give you one comprehensive overview over the messaging feature area, even if that clip is going to be fairly long. So you can go to it, and then down here in the blog you can actually see some time codes for the several sections, so you can go and skip ahead to those. So we're going to talk specifically about the messaging capabilities of Service Bus, but in the beginning, let me just give you a brief intro what Service Bus is if you're not familiar with it yet. It's a cloud-hosted or self-hosted messaging middleware that we produce at Microsoft. It shows up in two variants. There is the Windows Azure Service Bus that we host in the cloud as PaaS, Platform as a Service, inside of Windows Azure, where you simply go to the portal and you can go and create yourself a namespace that then can contain entities, queues, topics, notification hubs, relays. And so we're managing all this for you. We manage the storage and you pay for it on a per message basis. I'm going to talk about that in detail in a little while. And that service lives and is available in all Windows Azure data centers. And there's also some extras. For instance, there's an Office 365 version of Service Bus that we kind of host extra, that the workflow service of Office 365 sits on top of. So that's kind of an extra little thing on the side that we have, but it's also running Service Bus kind of as a platform, as a service because Office 365 is so large. In each data center, we have a set of clusters, multiple clusters. We do that so we can upgrade them one by one, and also that's how we manage capacity. If we need more capacity, we stand up more of these clusters. And the same technology that we use in the cloud, the same messaging engine that we use in the cloud, is also available for you to download and host yourself in the form of Service Bus 1.0 for Windows Server. And that's something you can get from downloads.microsoft.com. Search for Service Bus 1.0. And that's a downloadable package that you can download, install, and then configure. And that gives you the Service Bus messaging engine. So exactly what we're discussing today. It's going to give you that as an installable product. That product is free. It's free for use with Windows Server. We support Windows Server 2008 R2. And we also support, of course, Windows Server 2012. For development purposes, you can run it on Windows 7, and you can also run it on Windows 7 Service Pack 1, that's important, and also on Windows 8. Supported are only the server version, so if you want to run it in production, you must run it on top of Windows Server. What it also needs, it needs SQL Server. It runs on top of SQL Express, so you don't have to. It's a free offer, so you can go and install it on top of SQL Express and install Service Bus on top of this. So what you need to go into production in the smallest scale is you need to have a Windows Server standard license. And we support anything up to a SQL Server 2012 always on cluster, so the highest configuration you can build with SQL Server. We're running on top of this, and really what you need to have in terms of reliability, storage reliability, depends on your SQL setup. So if you want to have the maximum storage reliability, then you can go and go as high as a SQL Server 2012 always on cluster. The messaging engine that we ship in the cloud and on premises is largely symmetric. It's the same code base. However, since we only ship the server code base about every 12 months, the server code base will lag behind. We follow the principle of cloud first, which means we're developing all features first in the cloud. We deliver them first in the service, and then we effectively migrate them out to the server version. We effectively fork off the server version for maintenance, and then at some point we're forking off a next version and merge that with the capabilities that we need on premises, specifically for configuration and installation, etc., etc. So the server will always lag the service for a bit. For instance, The AMQP protocol that I'm going to talk about is going to ship very soon on the service, but it's going to lag a bit, probably towards the end of the year, for this delivery in the server when we ship the server the next time. Overall, Service Bus has 3 large feature areas: pops up reliable messaging that I'm going to talk about today, and the relay, which allows you to expose a web service from anywhere to anywhere, and that's going to grow closer to some of the capabilities that I talk about here over time. And also we have the new notification hubs, which are discussed in several videos that I have on the blog here already. So Service Bus brokered messaging has 2 large pieces, 2 entities that you can go and install and that have their own APIs. You can create a queue, or you can create a topic and subscriptions for that topic. A queue is really an ordered message log that has different ways of how to get at the messages once they're in there. So let's talk about the message log first. The queue gets messages in, and they're ordered by arrival. So the broker kind of plays the judge on which message was first in the queue, and then orders them by that. It stamps every arrived message with a sequence number, and that's a monotonic, gapless sequence that the broker guarantees. It also stamps every incoming message with a timestamp that's managed by the broker, where you have now an authoritative clock. So for instance, if you have a business case where you have a certain cutoff time by which messages need to have arrived, but you're not able to process all the messages at that point, you can use that clock. You can use the NQ time UTC property on each message kind of to play the judge on whether a message arrived before a particular point in time or not. All the data that comes in is being stored transactionally in a backend store backed by SQL. So we're using the SQL database in the service. While you will use, if you install SQL, if you install our server with SQL Server, it will store the data in SQL Server. And what we guarantee with this is that we get for your data, for your messages, the same reliability assurances as we get from the underlying database. So if you install it on a single node SQL Express database, and you have this on a single disk, if you lose that disk, well, then the data is gone. If you have it on a RAID setup, well, then you get failover and more storage reliability from that. If you do a multi-node failover cluster, well, you get even more reliability, and you can use the SQL 2012 features. In the cloud, in the service, we use SQL database with all of its failover capabilities, so we get super reliable storage for your messages. And every message, at this point, every message that we send into the system gets persisted before we come back to you and say, yes, we have accepted the message. There are 2 modes in how we deliver messages out. The first mode is the traditional pull mode for a queue. So you come up to the queue and you ask for a particular message, and and then you pull one message out, and then you pull the next message out as you can go and process them. The other delivery mode is forwarding. So you can push messages into a queue, and then we will go and forward that message as it has arrived to another entity inside of Service Bus. Topics have all the same features that queues have. So they have the same kind of notion of a message log, and they have the same kind of operations that are being done on ingress on the messages. But they have multiple outs. So a queue has a single out. It has a single, effectively, cursor that runs over that message log and kind of traverses the message log by sequence ID. The topic has multiple of those. So you can go and it starts out with none. It starts out with no subscription. So messages that go into a topic with no subscription have no subscriber, no interest, and therefore basically just get instantly discarded. As you add a subscription, you add another head, another cursor that can now go and scroll over that message log. The effect of that is, as you see here on this on the picture, is that if we have 3 subscriptions, we get 3 independent views over that message log, which means you send one message in and it becomes eligible for each of these 3 subscriptions. So you can do broadcast to all of them, or you can go and do filtering, where you have conditions based on which you can go and select messages out of the subscription. And we're going to get into details on all of those things. So the subscriptions are named and durably created. They have, and that's a brand new feature that's currently only available in the preview assembly. If you get this with NuGet, you can get our 2 versions of the SDK. One is the production version of the SDK. You search for Windows Azure.ServiceBus in NuGet, production version. It's also chained in with the Windows Azure SDK. That all, if you're developing on .NET, obviously. And then there's a ServiceBus.preview assembly that's also a NuGet package, which always has the newest things. So it has the AMQP features and has features like the one that I'm just mentioning. And that is the optional expiration of subscriptions. So you can go and create a subscription and then you can set an expiration time for it. And if the subscription is idle for longer than that expiration period, the subscription will simply clean up itself and go away, which is good for cases where you have a setup with a dynamic cluster. You create a subscription for a particular node. The node crashes. Well, if there's no activity from a particular node, then the subscription is going to clean up itself after, let's say, 10 minutes or 20 minutes. Or if you have other dynamic clients, they can now subscribe and you don't have to go after them and go and do that cleanup. Otherwise, they're going to stick around. The subscriptions, they're durable objects if you don't set that expiration time, and you can have up to 2,000 of them. The recommendation that we have is that you start partitioning your audience much earlier than 2,000. Each subscription has impact on the flow rate that you can get through the topic. And what that means is that you have if you have a queue, and the queue has a throughput of 2,000 messages per second, you can get a message in and you can get a message out, and the flow rate is going to be the same as the throughput, which is 2,000 messages per second. If you have a topic and you have 2 subscriptions, now you're making 2 copies of each incoming message, which means you have a total throughput of 2,000 messages per second or 1,500 messages per second. But then, since you're always making 2 copies, the flow rate is only 750 messages per second because you need to make 2 copies, you need to push 2 messages out. So the mechanics are such that the throughput capability of an entity, that's kind of gated by the underlying mechanics. And so the flow rate that you're going to get is effectively total throughput divided by the number of subscriptions. It's not exact math. The subscriptions tend to be a little bit faster than that simple arithmetic. But that's a good notion to live by. Now, how you get to partitioning, how you can do that is by using that forwarding capability to create dissemination trees for messages. And I'm going to talk about that more as we get further in this talk. Each of these subscriptions can filter, so this is why you see kind of the gaps here in the sequence. And it can filter based on conditions over the content, more precisely over the properties that are in those messages. Sorry. And the conditions can filter, and the rules can also modify messages, so they can go and effectively do some simple manipulations, and they can also tell you which of the rules has fired. From a protocol perspective, but also in how you can deal with them from a program, is the topic tail, where you enqueue messages, looks exactly like a queue, and the topic head, the subscription head to be precise, also looks exactly like a queue, and they're protocol compatible. And we have anonymous data classes in the SDK, and that's also true for most of the other language SDKs, and also true for the protocol, where you can go and receive messages independent of what that entity is. So you can start with a queue, and then you can go and make that into a topic, or vice versa. That is completely interchangeable. It's just a matter of how you go and provision your system, and then how you feed addresses to your application. And if you're using these abstract receivers, message receiver or the abstract sender, message sender. Then you can treat the topics and queues and subscriptions very much alike. I've so far talked about some classes that are available in the .NET API, specifically in the .NET Service Bus Messaging API. That is the most featured API that we have, and kind of all the features go there first. And that's mostly a function of where we currently are in terms of protocol, and that's going to change over time. So let me tell that story quickly. So we have applications, and those applications talk to Service Bus. So there's a number of options that we have to make that communication happen. On the Windows side, we have two main APIs. We have the Windows Communication Foundation API, so we provide a net messaging binding. That binding is equivalent to the MSMQ binding that you find with WCF. So if you're building WCF applications, if you're using the Windows Communication Foundation for your solutions, then adding Service Bus messaging support is as simple as adding the net messaging binding, and then there's an automatic pump that will go and receive messages for you and serve them up to you, etc. So that's all there. That works with SOAP messaging, and is largely really equivalent to the MSMQ binding. MSMQ, by the way, the Microsoft Message Queue is a technology that we also own in our team, and that's effectively our legacy technology that Service Bus is going to replace over time. We don't have full feature parity at this point, so MSMQ is being serviced. It's also going to be in the next version of Windows, so no need to worry if you're an MSMQ customer. We're going to keep servicing that infrastructure for the foreseeable future. The other way of talking to Service Bus is through the Service Bus messaging API, which you get through the assembly, the .NET assembly that's in the Azure SDK. So that's Microsoft.servicebus.dll. The namespace in the .NET languages is Microsoft.servicebus and Microsoft.servicebus.messaging, specifically for the messaging capabilities. The WCF capabilities sit on top of that API, so they're just effectively shim over that API. That's kind of the native API. And underneath this, as you can see in the yellow, is the SB messaging protocol. That's a proprietary protocol that's sitting on top of WCF NetTCP, the Service Bus SBMP, as we also call it. And that's the current primary protocol for the .NET API for Service Bus. Well, you also see below this is the AMQP 1.0 protocol. And that's the future protocol that we're going to standardize everything on, that effectively we're going to migrate to with all the features. AMQP is an effort that has been started several years ago. And this year, late last year, this was ratified as an OASIS standard. So now it's an open standard that's supported by a large standardization organization in the industry. And we're also pushing that further with the whole consortium and with OASIS to become an ISO standard for interoperable messaging. That gives us enough of a foundation, a good foundation, to actually go and make all of our features available in a fashion that they're interoperable with a broad number of platforms. So there's Service Bus messaging protocol, which still has some features that we don't have in our current AMQP implementation. We're going to have the AMQP implementation catch up and effectively then phase out our proprietary underlying protocol and make it completely open standards based. That opens up a whole new set of capabilities and opportunities on the other side of the world, the whatever side of the slide that I have here. We're working very closely with the Apache Foundation, the Proton project, and also the Qubit project through my colleague David Hingham, who's also on the Service Bus team and is co-editor of the AMQP 1.0 spec. To make sure that those libraries, those open source efforts, interop nicely with Service Bus. So we do active testing, and we try to make sure that with that we have a way to reach into embedded devices, into C, C++ programs, PHP and Python sitting on top of Proton C have been tested to work, and also the Java JMS capabilities in the Apache Cupid stack setting on top of Proton have been tested to work against Service Bus's AMQP 1.0 head. And as we extend the features of AMQP, of the AMQP implementation that we have on top of Service Bus, as we add kind of our additional features in there, we're also going to show you how to leverage those on these other platforms with those other libraries. And then to be even more interoperable, we have and have had for since Service Bus exists an HTTP head. All the management operations that you do on Service Bus happen on HTTP anyway. So creating a queue, creating a topic, managing the subscriptions, all those things happen on the HTTP head. But HTTP head also obviously allows you to send messages, to receive messages, and that's a capability that's used by most of the other SDKs that we ship for Windows Azure, so the Python and the PHP, the Node.js client, they all use the HTTP path, which is almost as featured as the normal proprietary path is. It has some features that are missing. One of them, most notably, probably is the two that are most notable are sessions and transactions that are missing due to the disconnected nature of HTTP. And of course, if you have any other client that can talk HTTP, the HTTP protocol is completely documented on MSDN, so you can go and implement a client on any platform that has HTTP, for precise HTTPS support, because we require secure communication to Service Bus. So the three connectivity options, already mentioned them. I'm going to revisit them quickly, also in order to tell you what the ports are that we require. If you talk to us from outside of Windows Azure, if you need to open up a specific outbound ports, we are communicating through the standard ports on AMQP, so that's 5671, 5672, preferring obviously AMQP-S. That's going to be the preferred, likely the only protocol that we're going to really support, 5671. AMQP-S and AMQP differ in the exact same way as HTTP and HTTPS differ, and that is that HTTPS and AMQP-S first open up a socket, overlay it with TLS, and then start the protocol. And that's simply just much simpler than doing an inline in-protocol TLS upgrade. The SBMP protocol that I talked about requires port 9354 that needs to be open. We also have a way, and this is one thing that we can do with our proprietary protocol, is we have a dual socket HTTP tunnel capability, so we can get out through port 80 and port 443 if port 9354 is not available. We're also working with the AMQP consortium with folks in that community to put AMQP on top of WebSockets. That's an ongoing effort. And once that's kind of standardized, or once we have a good solution for this, which is going to settle, then we're also going to plumb that into the Service Bus gateway. The HTTPS protocol, no surprise there. TCP port 443 needs to be opened for that purpose. And we also need port 443 to obtain tokens from the access control service that's associated with Service Bus. And of course, their HTTP is based on RFC 2616 and RFC 2618 for the HTTPS features. The messages that we send around are very similar to the normal internet message format. We have a notion of headers or properties and an entity body. That similarity makes a lot of sense because it's used in most protocols. What's important, if you're coming from WCF, these messages are not SOAP messages. The headers are not SOAP headers, but they are effectively just key value pairs. And we differentiate between two kinds of properties. We have system properties and user properties, or custom properties. And it's actually not uncommon in messaging to have messages that carry no body, no entity body with them, but where all the data is expressed in those simple key value pairs. The advantage of that is that the broker can see them and that it can actually operate over them if you're using rules or if you're using filters, as I'm going to show you later. The messages have limits as we can accept them. Those limits that I have here apply to the service. In the server, you can actually tune the maximum message size, and you can go and make this larger if you want to. But in the server, we chose to make the maximum message size 256 kilobytes, which is probably not very large, but which is, once you think about integration of services, sending data around over large distances with bad connections, bad network connections, then 256K is actually already quite a bit of data. So we chose to make it 256K so that we have it easier to go and deal with scalability in the system. We can go and reroute messages without hauling too much memory around. We can keep more messages concurrently in memory. So it's a decision that we make because of the scalability of the backend service, but it's also a decision that we make because of the amount of money, the amount of memory, the amount of bytes you would have to resend if we're losing a message on the wire. So it's a trade-off decision, and the trade-off decision arrives at an arguably arbitrary number that is 256K. If you need larger messages, there are ways to do that. I already mentioned sessions. There are also a mechanism to do this, so I'm going to go and mention that later as well. The total size of the properties must not exceed 64 kilobytes. And so the maximum size of the body is 256 kilobytes minus the properties, user properties and system properties together. Each property doesn't have a hard limit. However, since we're mapping them from and to HTTP, depending on your protocol choices, they're limited to the factual limits that HTTP and the respective HTTP infrastructures give us. So it's good to keep the properties under 4K in size, and it's probably even wiser to keep them under 2K in size, even though we don't have any really particularly hard limits. We don't have those limits that we impose on the server, but as you go through HTTP intermediaries such as proxies or your own development stacks, they might actually go and have quotas. They have gates on those. So as ambiguous as HTTP is, because that doesn't have hard limits in the specifications, as ambiguous are we. We support effectively any size within those quotas. However, the recommendation is that you keep it to 4 kilobytes or less as values, this part of any individual property. The messages the messages in this way are an abstract model. We're mapping them from and to our protocol heads. So Service Bus has, as you may remember from the introduction from the programming model options slide, multiple protocols, AMQP, SBMP, and HTTP. And the messages need to be interoperable between them. So you should be able to go and send us a message over HTTP and get it out over AMQP, or send it via SBMP and get it out via AMQP. So what we do is we have an abstract message model, and we go send messages to one protocol and then map those over. The goal is also to keep things very simple. So in the simplest case, when you send us an HTTP message, we will take all the headers that are coming with an HTTP request that gives us a message. We'll store them as user properties. We take the entity body that you send us as you're posting the message, which is a simple post against the tail of a queue. So the queue has a messages collection, and the messages collection can take a post. So we take that message, and we take whatever you give us, and we store that in the queue. Whatever headers you pass with that become user properties. So that we make it very, very simple, and you can actually go and get them out at the other end. So the HTTP message, or the headers, as you can see, map into custom properties. And we have a special header if you need to set from an HTTP request, if you need to set the time to live, you make a little JSON object that contains a time to live property that's set to a value, a number of seconds. And then you pass that inside of a JSON object. You pass that to us in a broker properties header, and then we're going to go and translate that. So we have one special header. The format is actually documented, obviously, on MSDN, and you can go and pack all the control properties for the broker into that one property. So we give you effectively maximum leverage and maximum flexibility on the customer header, so you can set. So we reduce the number of clashes on potential clashes that we have on significant things that the broker has. And then, of course, the entity body maps straight to the entity body in the message, in the service bus message. And we have a special system property called content type. So the content type property maps straight to the content type. So we actually flow the content type over, and we also give that back to you. As we surface a service bus message up to HTTP, we do the same mapping in the reverse, which means we take the custom properties, we map them into HTTP headers that we return to you, and then we also give the body back. There's a number of property-specific HTTP headers that we filter out that are illegal effectively for us to play back. Those are primarily around connection management. So anything that's just a peer-to-peer header in HTTP, we're effectively intransparent for on the HTTP path. On the AIMQP side, the AIMQP model is something that we've been working on for a long time. So there's a notion of system properties, broker-specific properties, and also custom properties and a body that is very well aligned with what we do in the broker. And therefore, it maps fairly directly from one to the next. So there's no significant difference from that perspective. All the concepts that are in the AIMQP protocol kind of map straight up into the implementation that we have in the broker in Service Bus. If you're using WCF, if you're using the net messaging binding, then your SOAP message, which has a fairly similar structure, right? It has headers and it also has an entity body. That whole SOAP message gets serialized and then gets stuck into the body of a brokered message. If you want to set properties on the brokered message, there's a brokered message property that you can use with WCF. That's actually in the Microsoft.ServiceBus messaging namespace. It's a special property that we have there. And that you can go and add as a property on the outbound message properties in your operation context, for instance. And with that, you can explicitly go and promote values out of your application context into broker properties, either custom properties or also into system properties. So we're sticking effectively here with the WCF model where if you want to influence the transport headers, you have a special property that you use for that. It's the same model that we use for HTTP and WCF. And otherwise, the SOAP payload goes entirely into the body of the message. So that's how those things map. It's not the same. It's not a one-to-one mapping as we have with AMQP or HTTP. It actually is a mapping into the body of the message. And of course, as we go and restore the messages into SOAP, we do the same thing in reverse. And we also go and take the message properties that come out and stick them into the brokered message properties property bag and make them available on the message properties that you can typically in the typical WCF app get through the operation context. There's two key delivery options, two key plus one additional option that we have. One is receive and delete. You can come to us, you can make a message receiver, or you can also use the HTTP API in this way, and you can walk up to us and simply say, receive, with a receiver that's configured for receive and delete. You will get a message. As soon as that message is removed from the broker, we will go and delete it out of the broker. And if anything happens on the way, that message will be lost. But it's faster because it doesn't require an extra round trip. And HTTP, it's a delete operation. So you do an HTTP request to the head of the queue. So you have a queue that has a messages collection that has a head /messages/head, and on that you can do a delete, and that will take the first message and deliver that back to you. So the delete actually has a entity body comes back. That's where the message is being delivered. That's a very fast option, but it is potentially lossy. The non-lossy, the more reliable, very reliable option is peak lock. You walk up to us and you say receive, and you can do the same thing with HTTP as well. You say receive, you get a message, and we hold that message kind of on the side and we lock it. So we make it invisible to anybody else. Whoever comes next will get the next message in the row. So this is being hidden, and we give that back to you. Now you can go and process that message, and you can decide whether you are happy with your processing result. And if you have processed the message successfully, then you come back to us and say complete. In that case, we remove the message. If you say abandon, then we're going to remove the lock and make the message visible again so it can be delivered to whoever is the next receiver who is in the row, which might be your same program or someone who's receiving concurrently on that same process. If the receiver crashes, well, then there's a lock timeout period that expires. As soon as that timeout period expires, the message also gets released. That will cause things to potentially get out of order because you have one message locked, the second message is being delivered to someone else. The second delivery is successful. The first delivery runs into a crash or into a situation where the message needs to be abandoned. Now that reappears in the sequence, and now you have a message that was actually enqueued earlier, which now gets processed later than this one. That is often not a problem. If that ever is a problem for you, if you need absolute order in processing, you can use sessions and label all the messages that are coming in with the same session ID, because sessions, and I'm going to explain that feature a little later in more detail, will go and lock not only that one message, but it will actually lock all the messages following it with one shared lock, which means we give you absolute order even in these situations. There's two kinds of receive operations in brokered messaging. The first one, and that's used by AMQP and SBMP, is a credit-based model where you simply call receive as many times as you need from a client, and that happens over typically a shared connection. But none of these receives sits there and waits for a reply. It's effectively an independent operation from the actual act of receiving the message. So the client API effectively registers a credit with the broker on the other side. And then the broker is waiting for as many messages. There's 10 pending receives, it's waiting for 10 messages, and then services them to the respective logical request thread as they arrive. The receive operation is being demuxed kind of on the client. So it is not a long pull in that sense, but it's really the maintenance of that connection is completely independent of the maintenance of any individual request. You can go and park a request like a batch receive for 100 messages altogether. And it's simply a matter of registering how many messages you want, and then the broker doing like the accounting on the other side of how many messages you get assigned based on your needs. So that's one model, and that's the model that we use in AMQP and SBMP, with which the protocol gets full duplex and fairly efficient. With HTTP, we can only ever ask for a single message, and then the message gets delivered. And then we ask for a message again. So you need to have multiple connections for that model. And you can on one connection, you can only ever request one message. And with the SBMP model, we can park a single request for 100 messages. And then 100 messages are shooting down that pipe. And probably if there's an interleaved request, 50 messages come from this request, one comes from another request, and 50 further messages for the other request to satisfy its needs. So it's a duplex protocol, much more efficient for that purpose. So we have that in the SBMP. We're also going to have the same model in AMQP. So that tells you already from a efficiency perspective, AMQP is going to be a much more efficient protocol than using HTTP for messaging. The server that we give you is free in the sense that you own managing it and you own running it. That will come with its own cost. If we run it for you, if you give us the honor of running that for you in the cloud, this is our pricing model. We charge you $1 per 10,000 messages. This is US pricing, current right now as of February. 2013, 1 US cent per 10,000 messages, or $1 for 1 million message or transactions. And the message transactions function as follows. If you send us a message and the message is not larger than 64K, that's one transaction. So that's very simple. Every further 64K segment also counts as a further message. So if you send us a message that's 256K or even 250K, that is 4 segments of 64K, 3 of full 64K, 1 with a fraction of 64K. So these each count for one message transaction, so that's 4 transactions. So the easiest way to remember is send one message, 64K is the limit, one message transaction, any further 64K, also beginning 64K is also one message transaction. If you receive a message, again, receiving that message 64K is another message transaction, same for the additional frames, same charging model. If you long poll, we charge for, so HTTP, we charge for every time you come to us and come also back with an empty frame. So it's not necessarily payload frames, but also an empty frame. If you make a very busy poll against us, which is not so good for our system, then we penalize you by charging you for every time you come back with an empty request, which means we encourage you to actually do the long polling with the maximum limit, so about 55 to 58 seconds. And with that, if you have a very low throughput queue or a very low throughput topic, you will have very low idle traffic. You can go and calculate this if you say 24 hours, 60 minutes, and then you give it a little bit of slack. That's not a lot of messages based on this pricing that you have to pay for, even just for a nailed up idle connection. That's not the same. The messaging model is a little bit different there for HTTP. If you're sending data out of the data center, so you are receiving to a client that sits out of the data center, you also need to go and look at the surcharges that we have per gigabyte. If you're not sending huge amounts of data, that's not going to play a very significant role. But anyways, you have 5 cents to 12 cents per gigabyte. Starts at 12, obviously, and then goes down to 5, depending on how many terabytes you're sending. And the same thing is true for Zone 2, but in Asia, that's mostly the Asia DCs, or it's the Asia DCs, but the charges there are a little higher because that's how the market prices there are for traffic. With that, let's go and talk about some of the messaging patterns that we see. I'm not going to spend too much time on the patterns part, but it's kind of important to motivate some of the feature areas. So what queues give you, and the same is true for topics, is a number of key capabilities that I'm going to go over. First one is load leveling. The receiver on a queue or on a subscription will typically do a pull that is coupled to a processing motion. So it will go and get a message, take the message, process that message. When it's done with that processing, it will go back and get the next message. So it will couple its load, it will couple its work capacity to receiving the message. So it will only get as many messages as it can actually work on. The sender may send based on a completely different pace. So for instance, it might be that you have a shopping scenario where messages are being delivered for end of day processing, and they come from all of your branches. The whole day, everything is quiet, and all of a sudden at, let's say, 8 o'clock in the evening, you get tons of messages in that need to be rolled up for the daily report. Now, if you have this, the receiver at the other end only needs to be able to deliver from 8 to, let's say, 12. It needs to go and roll up the data and produce the result, but it doesn't need to go and deal with all that load, all that spike during that 1 hour. So what the load leveling capability of the queue does is it allows you to kind of push a burst into the queue gets longer and longer, and then you can leisurely kind of go and eat into the backlog and go and roll this up. So it levels the load out. What it also does, and that's kind of the end of day processing is a good example for that, is it allows you to do batching and offline. You can load up a queue with data and only show up every hour or probably once a day and go and get the data out and process it. And the queue will always be there and the queue will always be listening, but your backend process that's actually doing the processing doesn't have to be. This becomes more obvious even in mobile scenarios where you use a queue, or rather a subscription, as a mailbox for an app that sits on a device. The app will not always be on. The app will actually be very rarely on, just a matter of minutes or seconds a day. So if you want to send messages to such an app, you will go and deliver the message into a subscription. The application will then start, walk up to the subscription, get that data, and with that always have an available delegate, if you will, in the cloud if you're using the cloud. So it's also very suitable for offline connectivity. Because the queues allow competing consumers, and the same is also true for subscriptions, and because of this model of coupling your capacity, your ability to do work, to receiving new messages, this also gives you true load leveling. True load balancing. Load balancing in the sense that you make the distribution of jobs truly depend on the capacity that you have in your system. And you can actually go and observe how much work capacity you need by observing the length of the queue. If you contrast this to the network load balancing capabilities that you find in many systems, they're spraying effectively requests across machines, and they're not so sensible to the actual work that's being done here. This is very different because the machines will go and just pick up the work that they can safely process from the queue. If the queue gets longer, you know that you don't have enough workers, so you need to go and add some. If the queue is very short, if there's nothing in there, you can probably go and collect some of those workers again. The queue, let's stick with the scenario that I had with the end of day processing with many branches that you have, many shops that you have, is also good for fan-in. You have a single queue. The queue kind of collects the data from many different external sources. It acts as a gateway for a service, and that service then gets the data in. So you can let it act as a concentrator. And once we talk about forwarding, I already talked about that in the very beginning, if you remember. Then that even gets more interesting when you think about multi-stage aggregation, when we talk about roll-ups, how we can go and take some data, accumulate results over data, and then take that accumulated result and forward it further. If we do this, and we do this in a fan-in tree, we can build 4 very large setups with super scalable setups, very efficient ways of reducing data and giving you consolidated roll-up information in a very timely fashion into central systems. With topics, you can do a number of additional things because you get one message in and you can get multiple messages out, one on each subscription, actually multiple on each subscription if you want to, with those rules. So that first gives you message distribution. You can send one message in and get 3 messages out, one for each subscription. But you can also go and constrain this message distribution by making rules on the subscription which are selective about the messages that are allowed to pass. So the first thing is filtering, where you go into the message and you go into the user properties or into the system properties of messages and run a condition over them. So for instance, here is a rule, one out of at most 2,000 rules you can have per subscription. It's typical that subscriptions have only one of those rules, and you have, for instance, name, like, v, percent. So all the last names here in this case that start with V, like mine, would then be eligible for this, and all the messages containing anything else would not be eligible for that particular subscription. So every rule that matches yields a message copy, and it yields a message copy because there are also actions associatable with those messages. I'm going to get with those rules, and I'm going to get to those once we get down to those features. So there's a SQL 92 kind of language. I'm also going to show you that a little later. Partitioning is another facet of this use of rules. You can have 3 partitions, and you have a partitioning criteria. You have a partitioning space, let that be the alphabet, or let that be numbers from 1 to 10,000 that you create a hash over, or some random number over. And then you have partitioning rules, which say if the incoming message has a partitioning number from 0 to 272, then go and assign it to this receiver, etc. So you have mutually exclusive rules, which allow you to go and do partition fan out to a number of partitions in your system. The nice thing about this, if I go back quickly, is that the sender doesn't need to be aware of that partitioning at all. The sender just sends the messages, and the sender can be oblivious to the partitioning. Actually, the receivers might also be able to be oblivious to the partitioning, and you can go and change these rules on the fly, and actually be able to change those rules in the context of a single transaction. So you can make multiple rules change in one simple transactional set, so that from this point on, the rules are going to be changed for any further incoming message. Out of these basic patterns, you can compose some additional composite patterns. I have a selection here. One is update read separation. You have if you want to have a separation between data that comes into your system that might hit multiple kinds of stores. So you have the data is pre-validated in some form up here in this corner. And then that gets sent to the topic, and from a subscription goes through a reader into the first database, which is a projection of that data in some form suitable for these clients. And then you have the data go into a master database, which is suitable for projection of for these clients. So you can go and effectively separate those paths. That's something that is a fairly popular pattern in the context of a architectural movement. It's called CQRS. There's a CQRS journey project that was managed by the Patterns and Practices team at Microsoft. It's an interesting book to go and read. Also, that approach is very interesting for how they actually went about doing that project. So you may want to go and check that out as well. You can find this with CQRS journey on searching msdn.microsoft.com. Another way to use topics is to use update notifications. Actually, our timeout or idle timeout feature that we have added to topics is going to help here as well. So you have a long-running worker, and the long-running worker is doing work. That's the thing with the W here. And that is seeded with some state from a database. It's loading state from a database. And now it's doing work, and it's scheduling work. It's doing, let's say, periodically executing some job based on some input. And now you want to assign in a new job. How does the worker learn about it? Well, if it's just database based, it will go and go over some database state and do a query to find new jobs. That's one way of doing it. The other way of doing it is to put the job, the details, really into the database, so that whenever a new worker starts, it can actually go and seed itself again from that data. But then to actually go and take the same set of data and route that through a topic into the worker. So the worker can either immediately find out about that job and never go to the database, or it can go and get at least a link to the job and then go and pick up the data from the database, which actually gives you less polling on the database and gives you less traffic on the database and low latency for picking that job up. Another common way of using these kinds of mechanics is to use service bus topics and also queues for the purposes of diagnostics and statistics inside of a system. You have statistics, diagnostics logs, information from a backplane of your services that you build, very many nodes, and you want to get diagnostics information off. You can go and fan this into a queue or fan this into a topic for a subset of your services, roll it up, and filter it out by let's say, a priority or by some other criteria, run rules over them, and also edit the priorities, assign new properties, override properties, if you will, through the rules capabilities that we have in there, and then can fan them out to interested consumers. Some consumers may be interested only in, if you're using it for diagnostics, for SEV1, very critical errors. Some will be interested in more, on a particular things out of a particular component. So you can build some really powerful diagnostics infrastructures based on the messaging capabilities that we have here. If you're putting Service Bus behind a website, for instance, but you have jobs that require that you have a paper trail, or that you have that you want higher reliability for, you can use correlation. You have a sender, let that be an ASP.NET page, and that sends through a queue to a receiver. It will go and note, there's multiple ways of doing this, so I'm going to give you a short way, and I'm sorry about the issue here with that little word wrap. The sender sends to the queue a brokered message. The brokered message contains in the reply to property the name of the queue that it wants to have a reply to, and it provides an ID. That ID is either a correlation ID or a message ID, and sends that to the receiver. The receiver then works on that job, and then turns around and sends the message to the indicated queue name here, and then with that indicated correlation ID into the reply queue, and then the sender, the exsender here, the client, goes and picks up that message. So correlation is something that where client and the sender and receiver both send one-way messages, but they're knitted together by some kind of a correlation mechanism. You can have that as a N-to-1 model, where you have N senders and front ends. You have an ASP, each ASP.NET thread may be one of those receivers. And then each of them has a reply queue. Or in this case, it would probably be rather, if you have a dedicated queue, it would be rather a ASP.NET node, so a front-end machine, that you send messages through the send queue to a backend process. Again, this could be multiple backend processes. We're going to get to that in a moment. And then you send them to the receiver processes the job and then sends that to a reply queue. This is the N-to-1 model is actually very useful if you have a constrained component at the back of this. So if you only have one thing that can go and process, or two things that can process a particular message, a physical thing, a printer, a machine, a camera that you want to move around, anything that is constrained because there's only one copy of it, and there's actually those physical things exist in the real world, that makes sense to put behind a queue. And if you want to control it from, let's say, a web page, which is not too uncommon, right? A lot of things are controlled through web pages. Then you can go and use that kind of mechanism to kind of guard control to that thing through a queue and then send the replies back. This mechanism is not necessarily slow. Queues are being said to be slow, but the round trip time here, just the mechanics of the queues on the server will be back and forth under 15 milliseconds, and on the service will be in the order of 80 milliseconds. So that's all doable, especially through the reliability, extra reliability you gain here. So that's a good price to pay. Because you have competing consumer capability, on the back side of this, so on the send queue, you can now also fan out to M different nodes. Each can go and do the job, so you can go and scale this up, as I said that earlier, and then go and send to the reply queue. There are actually 3 different correlation models that we can make possible. The slides were showing effectively the simplest model, where you have message correlation, and you're doing this with queues. So the originator sets the message ID or the correlation ID in the outbound message, and the receiver copies that ID to the reply. That's what we saw in the picture before. The reply is then sent to the originator, to an originator-owned queue. So the originator, the ASP.NET Node, the machine, that has a queue, sorry, and then that is indicated by reply to. That's what it's being sent to, and then the originator has a shared receiver on that queue, and then dispatches locally on that ID. That local dispatch may mean that you need to have a lookup table, and you need to have some threads that are thread management that assigns an incoming message to unblocks a particular thread. So that might be a little tricky if you're actually doing that from ASP.NET, if you're doing that from a multi-threaded with a multi-thread environment. You can also go and make this with a subscription where you don't have individual queues, but you have a subscription on a topic. So the messages are sent back to a topic, and the subscription to which the response should be routed, that gets a filtering ID on that particular correlation ID. So you can create a correlation filter on the topic subscription. You can, or actually add a rule, to be precise, on that subscription filter. And you can actually do this in the context of a transaction. So you can set that rule, for getting back. You can all send that on the same transaction. And then session correlation is what I usually recommend, is the capability of setting the reply to session ID, and the receiver, all the receiver does is it sends to that session ID to a well-known queue. That queue may actually be shared across a number of nodes, and then the node is using a special function of the session API. It's picking up messages by the session ID, and I'm going to show you an example of that a little later. So there's multiple ways of getting that correlation work done, and one is just by using the queues, the other one is by using topics and rules, and the other one is by using sessions. We're going to take a look at the session model in a little while. The message correlation you use with if you have high throughput, when the work usually completes in minimal time, and if it's okay for the replying party to directly know the reply queue. The subscription correlation, if the replying party doesn't need to know or should not know the destination, then you can use the rules of subscriptions kind of as a way to anonymize the receiver and to decouple the replying party from the receiving party. Or if you are sending out a job, but there's a risk that your sender will die away, then you can actually go and use subscriptions to kind of reroute to a different receiver, to a different subscription. You can actually go and move this up and down. And then in session correlation, if you need to have things fast, if you need to have things multiplex, if you are using a highly dynamic environment like ASP.NET, if you have multi-threaded applications where a particular thread needs to get this, then sessions are actually the lightest weight subscription mechanism that we have, and that's the best fit. So with that, we're now going to get to the messaging features and go and walk through them one by one, with also looking at the respective code snippet. Most of the classes that I'm going to show you in that context live in this Microsoft.ServiceBus.messaging namespace in .NET, and we have the corresponding features also in the other SDKs. And most of those, and notably absent from those, are session support and transaction support. The rest of the features are generally there and involve usually setting some properties on this and that class, but I'm using the .NET API as a way to go and explain all the features. The features are implemented server-side, so they're implemented in the server or in the service, so you can use them effectively using any of those protocols with those two notable exceptions. So to send messages in the .NET API, you create yourself a queue client or a message sender or a topic client. I have a queue client here. And then you can go and send, and you can send a brokered message. And here I'm setting a label. That's a built-in system property that allows you to set a label on a message. That's a feature that's compatible, equivalent to MSMQ. That's the only really settable freeform property that you have on MSMQ. And I could also send A free-form property is as I do here on the property bag with the purchase order ID. And you can also see here that I'm setting the time to live and then send it. I'm showing here the synchronous APIs. I'm also showing the synchronous APIs throughout the rest. What we recommend in general, I have an extra slide on that as well, is that you use the begin and end send APIs generally, and also the begin and end receive API generally. Here's the receiving messages instead of using the synchronous APIs, because they're much more efficient. In one of the upcoming releases, we're also going to give you full task-based APIs, which means we're going to give you send async, receive async, and all those overloads. But they're actually very trivial to make from begin and end pairs using task.factory.fromAsync if you want to do that yourself. So receiving messages, as I said, there's two modes, receive and delete and pclock. I explained both of them. So you can create a queue client. I'm using here the variant of creating it directly from a connection string, which you can get from the portal. And then I create a receiver. On the receiver, I call receive, and I get that message. If the receive times out, so you can specify the timeout here. So this is a unbounded timeout. This will never time out. It will actually complete with an exception once you kill the receiver. So if you shut down the receiver on a different thread, then this will terminate. This won't terminate. This will block forever if there's never a message in there. Or if you cut the connection, obviously, then it's going to throw because any individual receive operation might throw, but you can also put a timeout here. And then if it's timing out after that time, then this is going to return null. So I'm going to give you a timeout exception, but because if you ask for a timeout on a receive operation, then coming back with no message is an expected thing. So we're returning null here. At this point, we don't want to go and hit you with creating a stack trace and all those ugly things that come with creating exceptions. In the pclock case, you receive the message, same model. And then obviously here I'm not testing, as you can tell, bad boy, for whether the message is null or not, which I should. But I'm doing that not because otherwise it wouldn't fit on the slide. So once I'm done with processing that message, I'm calling complete. That's going to cause an extra round trip to the server to tell the server that you're done with that message. So it's double the traffic. So that's important to know. But it is safer and more reliable. And here this abandon is telling the server that the data that this couldn't be done, and I'm doing an abandon and rethrow here. So I have no explicit handling, but at least I'm going to tell the server, hey, I want to abandon this. Again, there's asynchronous version of all of those things because they incur network traffic, they cause network traffic to happen, and therefore all those things should be async whenever you can do it, because that will make your process much more efficient. When the message gets locked on pclock, the setting is on the queue description. I don't have a survey of all the properties of the queue description in this deck, as you'll notice, but there's a message lock timeout on the queue description, which tells you which the default lock timeout is, and I think that's set by default to 2 minutes, or 5 minutes. I don't have that in my head right now. Excuse me. So the maximum duration, I think the default is 2 minutes and the maximum is 5 minutes. Now that I look at the slides. If your work takes longer than that, we can't make the lock timeout longer than 5 minutes. However, you can request extra time. So the recommendation for setting this timeout is to balance out things. So you have a typical duration for how long it takes you to process the message. Let's say 10 seconds, which is already an epically long time for most operations. You take a message and stick the contents of it into a database. That operation should really not take longer than a second. However, as things may go wrong, the database is slow, it has the hiccups, whatever it is, you have to retry. Let's say the normal time is 10 seconds. Now the clock has started, you're starting to process the message. Now something goes terribly wrong, and it exceeds those 10 seconds that you set as the standard lock timeout on the queue description. With renew lock, you can get yourself another 10 seconds or another 2 minutes, whatever the default timeout is on that queue description, you're going to get an extension by that default timeout. So you can actually go and keep processing a particular message, but if you crash, that message then becomes available again after that lock timeout. So you want to balance the timeout in case of a crash for when that message becomes available again against the duration of how long that takes, and of course the traffic this will cause. So renew lock, but renew lock basically puts you in charge of how long your process can take, and you don't have to worry about any collisions. You can send messages all in one go using a batch API. You can go and you can prepare a number of messages and then hand them off in one go. This operation is atomic. So if you send 5 messages, it will not partially fail. You will either go and send all 5, or you will fail altogether. Receive batch is kind of the same model. You receive all of those together. Receive batch, all the messages that you receive, you will get out singly, and they are individually locked. So if you have a log on the message, those logs will be managed individually. So you may want to go and make your batches small enough to get that data also processed in time. There's a feature. This is really if you need to send and receive messages kind of in chunks, and if you need to send and receive them kind of in an atomic fashion. We have another feature to go and increase the throughput, which is called prefetch. And I'm going to get to that in a little while. Topics have filters, as I told you. These filter conditions that you have on the subscriptions follow this. This is effectively the entirety of the syntax, so it's actually fairly lightweight. It's a SQL, as you can tell, SQL-derived syntax. You have implicit conversion, so if you want to compare a number, a decimal to an int, that's all automatically converted. There is a way to, if you are running into an exception, so these you can have invalid rules, obviously, because you give them to us as text. If there's an exception evaluating a rule, you can go and dead letter the offending message and again put it into the dead letter queue, which is something I'm going to get to. So let's get a forward reference here. So there's a way to detect what's going wrong and which message is the offending one. We have implicit conversion. For instance, if that goes wrong, if you're comparing a bool to a string, you have comparison, you have logic, and you have arithmetic operators. So you have you can compare things. You have and you have or, and you have plus and minus and multiplication and division, and you also have modulo, which is kind of useful. You can concatenate strings with plus. So if you have 2 properties which are representing strings, you can also add string literals. And so we have like pattern matching as available in SQL. And we also have set matching with in or not in, where you can go and check against expressions. So you can go and effectively have a string enum that you can check against, and then you can go and match those values. All the matches that we do here are case insensitive. And the way you create one of those SQL filters is by specifying it here, and then you can assign that to a rule. Paired with a rule, as I explained earlier, is potentially an action. So you can go and filter messages out based on a rule condition, and then you can manipulate it. So you can actually set properties in as you process them inside of a subscription. You can set and you can manipulate the properties of a message. You can't never touch the body, but you can go and manipulate those properties. So if a rule's filter matches, the action gets executed, and you can either set a property, which means you can create one and assign something to it, or you can override the value of one, or you can remove an existing property. So you can say remove property name, or you can say set property name, set full name equals first name plus space plus last name. So you can go and effectively create a new property based on existing properties. And that also allows you to do simple arithmetic. We don't have any functions in there except new ID, which allows you to create a GUID. So you can go and effectively create, if you wanted to, you can also create a new session based on this. So you have access here and also in the rules, also to all the system properties, which you can prefix with sysdot. You can get to all these user properties with user dot, but since we only have two spaces, we made one special sys, and user dot is an optional prefix, and you don't have to use that. So you have access to all the system properties. You can manipulate the time to live. You can go and manipulate the session ID. You can manipulate effectively all the properties that are on a message, and you can go and effectively turn a message that comes out of a subscription gets forwarded into another queue for purposes of whatever. You can go and even make that a scheduled message if you wanted to. Scheduled message we're going to get to in a little bit. Correlation filter, I already mentioned that for correlation. If you simply want to do a match on a particular ID, you want to do an equals, then you don't have to formulate a SQL condition, which also saves us the parsing. So you can, instead of doing a SQL filter, you can also specify a correlation filter. And the correlation filter has a label, and that's a name for it. And then you can go and make some conditions. So here I have the condition that is on the property name. There is the name Abhishek. And if that's matching in the incoming message, then this correlation filter will trigger. And that makes your flow rate higher because it's faster to execute. So this is going to make the topic faster for you. And you can go and match on up to 8 unique property names on a single correlation filter. If you set normally these rules on a topic, you will send the message in, and then you won't know whether the message is being distributed to anybody, because what we do normally in our normal operations, we take the message, save it to disk, and return to you, and then we start executing the rules asynchronously. If you turn on enable filtering messages before publishing, that's one of the shortest properties that we have, you will slow down the topic, because what you will do is you will execute all the rules across all the subscriptions before we give you an ACK. The advantage of that is that with this, you can know whether anybody picked up your message or whether the message fell into space, because we will throw no matching subscription exception in that case. So it makes the topic slower, because it makes your send operation, slows your send operation down. I mean, ultimately all the rules need to be executed anyways, but it makes your send operation slower, but it gives you an exception if we can't find a subscriber. It also kind of breaks the isolation between the send side and the receive side, but we have seen a number of use cases where that's actually very useful. So you can turn this on and off with a flag. It's off by default, and you can turn it on if you find that useful. Sessions, I've mentioned sessions a number of times, so let's talk about those. Sessions are enableable on queues as well as on subscriptions. And what they allow you to do basically is have multiple work sets, multiple message streams on a single entity, on a single queue, but also on a single subscription. The way you create a session is you send a message and you assign a session ID. The session ID is completely arbitrary, so it may be any arbitrary string. We don't constrain you to a GUID, and it can be something that comes out of your process. So you send messages in, and they now belong together by the virtue of having the same session ID. So one of the videos I have also here in this blog is an interview with the Halo team. So Halo 4 is flowing all their game statistics through Service Bus. So when you have kills and headshots and what weapons you use, all this, which shows up on Halo Waypoint, all that data makes its way through Service Bus. And the way this is done is collected on a per game basis, and the game ID from the console, it's actually used as a session ID, and this is how things group together. All the messages from the same game are flagged with the same game ID, and they form a session inside of Service Bus. And this is how they can be processed together by the same receiver. So a receiver now takes a lock on a particular session ID. It can do so anonymously by simply asking for any session that is not locked. So it will get, as soon as a message shows up with a unassigned session ID, it will go and be assigned to that. And then from there on, all the messages with that same session ID are being sent to that particular receiver. So you can pin a work set to a particular receiver, and that's a solution for doing large file transfers. So if you want to break the 256K barrier, you can do that through sessions. If you want to go and have a work set and have that being worked on by a particular receiver, you can do it that way. So with that, you can effectively take a session, take a sequence of messages and pin that to a particular party, and with that, load balance sessions across. To use sessions, you need to turn this on the entity level, on the queue. So the way you do this is when you create a queue with a namespace manager, you flag it as require a session. You can also do this through the portal, through the extra page in the portal. There's an advanced page on the portal as you create a queue, and they can also turn require a session on there as well. And you can do the same thing with subscriptions. On subscriptions, you also need to turn on the require session. Once you have this, then you can use the session APIs. Sending messages, as I said, is very easy. You simply make up a session ID and you set it. Sessions are not bounded, so there's no start or end to a session. That doesn't mean that you can't make one. It's just that we don't enforce one. So if you're sending a file, you can take the file name or a unique path, a unique a URI of that for that file, and make that the session ID. And you can terminate your own session. You can say, this is the first message, and this is the last message. And if you return the last message, then you effectively closed your session, you abandon your session receiver, and you're done. But we're not forcing you. So if you want to maintain a session for weeks, you can do that. And in fact, the workflow service that runs underneath SharePoint runs workflows, and those workflows might run for months. And they are managed through these boundless sessions. And so there's no time limit on those, and there's no forced end or begin. You can actually go and effectively model that on top of that yourself. Receiving is different. You don't call receive on the queue client. What you do is you accept a message session. The message session is a special object. It looks like a message receiver effectively, and allows you to receive messages out of the session. Once you accepted the message session, you will now receive only messages through that thing that have the same message ID and that the same session ID. And the session ID is pinned to your receiver, to your process, and through your socket on that service. So the service will only ever send messages with that same session ID to you. That's the pinning that takes place. What I show here is accepting a session with a given session ID. You would use that mechanism for correlation in, let's say, ASP.NET. So you would send out a message to a backend process that says, reply to session ID with that session ID, a number that you make up, make it good, and send that. And immediately thereafter, actually, before you even send that message, you say, accept message session with that session ID. So, and that can be a shared queue, and that queue can actually be shared across a number of backend nodes. So you say accept message session, you send your job off, backend processes, sets the session ID that is in reply to session ID as it sends back to the queue, and this will now go and unblock your message session receiver, which is now looking for this. It's effectively a one message subscription, if you will, and then you can go and pop that message off. And if it's not only one message, but 2 or 3 or 4 messages because the result is longer, then you do that for as long as you expect messages, and then you close the session receiver and you're gone. So that is a very volatile object if you wanted to, or you can make it a very permanent one. So it's a Swiss Army knife capability that we have in Service Bus. If you want to keep if you want to keep a record of the things that you've done, you actually have a way to do that. So let's say you have a longer running process, or you want to transfer, let's say, a very large file. So you have a receiver that takes messages in and saves those messages. Or let's talk about the use case that we have in the Halo game, where you have now multiple records that are coming in, statistics records that are coming in from the console, and they need to be collected until they can be submitted for processing, because Halo submits that game package, the complete statistics package, as one piece to the system. So what they do is they get a message and they need to remember it. And then they get the next message and they need to remember it. And then they get the next message. At the end, they get the final message and remember it. And then they have the package complete and they can hand it off for processing. What happens if that process now crashes that is handling the data? Well, it will have to fail over to a different node, that processing. So the lock gets released eventually. That's like peak lock. So then that session becomes available to another node. But how does that other node know what the state is? How far the processing has gone? Well, that's what the session state facility is for. You can get a message, you can do some processing, and then you can set the state on that session inside a service bus. So you can use service bus as a state management facility. And that's exactly what's being done in Halo, and also in Office 365 SharePoint. The workflow state is being held inside a service bus associated with a particular session. And once you're done with that session, once you're done with processing, you can effectively set the state back to null, and with that, clean that up. You have as much space as a single message for your session state, so it's not a huge bucket that you can fill, and it counts towards the total storage allocation you have for that particular queue. So storing the processing state is very simple. You get a message session, and then you can go and receive from that session, and then on that session you can go and set the state, and you can actually make completing that received message and setting the state. You can make that transactional, so that you can have a consistent update. I'm going to talk about transactions in a short while. To get the state out, once you have the session enhanced, you can actually get the state and you can manipulate it. If typically accessing the session state is bound to a receive operation, so you get to the state, you get to a message session once a message appears that you want to process. So the typical motion is accept message session anonymously without the session ID, then peek into the state, get state, dehydrate what the state is so you have some context, then receive the message, play that message, save the state again, and then effectively walk up to the next session. That's a typical flow. You might want to receive a next message. If you can't get a new message within, let's say, 20 seconds, you basically just go and walk away from that session and let someone else go and anonymously receive the next one. So that's the typical flow for that. If you want to get at those sessions to do some cleanup, to see what the session state is, what the state is of a particular process, because that's the state that you store yourself, you can go and do session browse. So you can go get to the client, and then you can get the message sessions here. And or you can actually go and get the message sessions that had changes within the last several minutes. And then you can iterate through those sessions and actually get to those, and also call get state on them. So you can go and browse through, and you can go and analyze what's happening in those sessions. If you need to do some edits, if you need to go and reset some state, if you need to go get some insight into what's going on in your system. So overall, sessions are a really powerful feature for multiplexing, for correlation, for workflow processing, for state machine management. That is being used in a broad variety of use cases that we see pretty fascinating things. So Halo and SharePoint, two very big properties using that feature, is actually something that's for us very exciting. Transactions are supported on Service Bus. We have local transaction support. We support transactions over single entities. So you can make things that are happening on a particular queue or a particular subscription transactional. So you can, or a particular topic even. So you can go and as long as you're interacting with a particular entity, all the things you're doing on that can be transactional. So you can go and get multiple messages a sequence of messages. You do batch receive, and then you can go and do 3, 4, 5 completes all in one go. And all those completes are going to be happening together, or they won't. So that's the transactional capability that we have. So message batches that can only be sent together, or storing state and completing a message. Things like this, you can go, so operations on a session, storing state, and completing a message. That's all things you can do transactionally. What you can do is enlist Service Bus into DTC. So you can't use the distributor transaction coordinator of Windows in conjunction with Service Bus. The reason for that is one of the reasons is that in SQL databases, Windows Azure, that also doesn't allow enlistment into distributor transactions. So it would be kind of odd if only Service Bus would allow that kind of capability using DTC. Now you could argue, well, you should do that then on the server. Again, using DTC is constrained in the way you can use the database. And also we want to have symmetry between server and service. So that's also making it really difficult. And there's a number of really scale constraints that come with DTC. So what we're doing instead is we're trying to give you as much transactional capabilities that we can give you in a symmetric fashion that we also know will scale. So we're supporting the standard transaction model. So you create a scope, a transaction scope, and you can do 2 sends together, and then you go and say complete, and those sends will now be transactional, which means they will depend on the outcome of the transaction scope. If you abort it, then the sends won't happen. If you complete it, then the sends will be dependent on that, and they will happen together or not happen together. If the sends fail, if one of the sends fails kind of on the server side, then the other will be also annulled. So it gives you a local transaction in the sense of a local transaction against SQL. Because we know that one of the most common scenarios for distributed transactions in messaging is to get messages from Q1, work on them, and put them back into Q2. That's kind of the bullseye scenario for distributed transactions with messaging. We have made that scenario particularly easy. So what you can do here is you can go and make a transaction across 2 queues with the help of one of the 2 queues. So you create a message receiver, and you create that over your source queue. And then you create a message sender to a target queue, but you tell the source queue really to do that handoff on the server side. So we're using kind of our source queue as the origin for messages, but also kind of as the transaction governor for sending messages to the target queue that you want to send to. So you have a message sender that sends to the target queue, but there's a transfer entity that kind of you send via, and that is the same as the source queue. Which means now the underlying operation, the transaction that we have here, runs only on a single entity. It only runs on the source queue, which the message is being posted to, secured on disk, and then being forwarded to the target queue. So we receive a message, and now we have some internal operation that processes the message. And now we send to the forwarder queue. So we send to the target queue. At least that's how we intended. But effectively, we do a transaction over the completion of the received message on that source queue. And we send via the source queue. So now we're binding that complete operation and that send operation together as one thing. And we're completing that here. The complete will depend on the send on that same entity. If that all completes, then we're going to do a transactional safe handoff on the server side from the source queue to the target queue, and with that have a proper handoff. So what we've done with that now is we have bound 2 operations together, a send, a receive, or more precisely a complete or a receive, but it's effectively a receive if you remember what the peak log model is. And that send, and that gives you transactional capability. And that's actually in Windows Azure, along with SQL Server, SQL Server's ability to do this across 2 tables within the scope of a transaction. The only capability to do that kind of transactional handoff and the only cloud messaging infrastructure that lets you do such a thing. Time to live is a feature of the broker that will allow you to make messages disappear once the TTL expires. So you can set that with the time to live property. You can set that to an arbitrary point in time. You should make it such that messages don't disappear on you without you being able to pick them up. Also, mind that there might be a backlog. So we've seen customers setting TTLs of 5 seconds without them being able to go and pick them up in time. So you should allow yourself enough time for latency. You should allow yourself enough time to actually catch up on your backlog. But they're good to triage between messages that are very important and messages that are not so important. If you have deadlines, if you want to have a timeout for an operation, and you want to be able to retry that operation after a certain time, so then set the message expiration time to 60 seconds, wait until the operation, if the operation doesn't materialize, if you don't get a correlated message back, well then go and set that, and so then send the message again after 60 seconds. The time to live is being set on the message, on the brokered message, so you can set that to a time span. And then the broker will turn that into an expiration time UTC, so it will actually give you the time at which the message will expire, so you can even respect that in your own process. You can actually go and make your processing dependent on that expiration time. If that expiration time fired while you do some processing, you might even choose to abort your transaction, knowing that the other side will now think that it will have to go and resend that operation. You can schedule messages to appear at a certain time. That's another time-based operation that we have. So you can tell the broker that you want to give it a message now, but the broker should only make that message appear at a certain point in time. You do that by setting the scheduled NQ time UTC to a certain time. So that then we're going to hold the message in the system. It won't be visible other than the accumulating in the storage quota. And you can also can't cancel those messages, so be careful. But at the point in time, we're actually going to make it materialize. The resolution for this is not precise on the millisecond, but it's within the realm of a few hundred milliseconds that we make those messages appear. So it's not a timer that's good enough for millisecond real time, but it's certainly good enough for any process, any typical business process timing. Dead lettering is a feature that's available on all subscriptions and also on queues. If you get a message and you don't know what to do with it, you can go and dead letter it. A dead letter is a queue that is exactly like a normal queue, except the only way to put data into it is by calling the dead letter function. It is a queue that sits on the side, kind of as a secondary queue on every queue and every subscription that we have in the system. So with that, you can go and take a message that you get, and the message is, let's say, improperly formatted. The body is improperly formatted. It contains invalid data. And you can go and have a safe place where you can go and put that message and say, I don't know what to do with this. And then you can put this into the dead letter queue. And then you can have another process which is looking at the dead letter queue and now goes and writes a report or does bubbles this up to a recipient. What you can also do is you can automatically dead letter based on TTL expiration. So there's a property that you can set on the queue and the property that you can set on the subscription, which will automatically dead letter a message if the TTL expires. So you could have a sender who sends into a queue also read on the dead letter queue. And the way you do this is you simply make a queue client over the dead letter path of a queue. And then you can go and get the messages out, and you can tell when the message has expired that was sent into the queue, so that hasn't been picked up, that hasn't been handled, and then you can go and bubble this up, or you can go and take some alternate path. Duplicate detection. For the cases when you, for instance, have a race like the one that I called out before in Time to Live, you send the message, and then you can't quite know whether the message has been processed or not, and you're inclined to go and send that message again. It would be a problem if you were sending a message twice and then it gets processed twice. Where it gets really interesting and dicey is when you have an HTTP path where you send a message in, and then the response, the HTTP response, that fails because of an intermediary failing, or that fails because of some other reason. So you have handed off the message, and that has worked, but then the reply kind of blows up on you. Same thing could happen in edge cases also with the other protocols. So what do you do then? Well, with the duplicate detection we have built in, you can actually work against this. You create some notion of idempotency for retries. So you can go and send a message. You set the message ID to a fixed message ID that you set up. If you send the message again with the same message ID, and it arrives the second time at the broker, we will take the second copy and throw it away. We'll do that during the duplicate detection history time window. If you set that, that's together with requires duplicate detection. If you set those two values, then we will start collecting the message IDs. And again, the message IDs can be whatever you like them to be. So they could be derived from your business process. They could be anything, as long as they're unique for the message. And then the duplicate detection will kick any subsequent message with the same message ID out if it arrives within the same time window. Prefetch, already mentioned that feature. That's an optimization. It's not like batching. What it will do is we'll actually preload the buffer on the client with an eager fetch as you start it up. So if you set this to 50, as we see in the example here, as you open up the queue client, as you start it, it will go and immediately go and receive 50 messages and try to get 50 messages into his prefetch buffer without you even saying anything. That is very fast. So it's much faster because it will go and anticipate that something that you will eventually call receive, and kind of decouples the factual network receive from you calling receive. It is also risky if you're using peak lock, because everything that has been fetched into that buffer needs to be consumed within the peak lock time, and you can only get to those messages once you have actually properly received them. So there's a balance to be struck in your application between throughput and processing speed. If you can process all the messages as they arrive over the network quickly enough, then prefetch is a wonderful thing with peak lock. If you are slower than what you can fetch from the network and you need peak lock capabilities, then at least keep the prefetch buffer relatively small. Prefetch will get the next message before you're asked for it. Auto forwarding is a feature that I already mentioned several times. That allows you to go and chain queues and topics and to scale out topics and subscriptions. So it has to do with scale out, it has to do with additional flexibility. It is about as flexible and powerful of a feature as sessions are. Probably even more powerful. What it allows you to do is a number of things. So the first thing I have here is a fan-out tree, where you create a topic. You have a topic with multiple subscriptions. And on each subscription, you set the forward to property, much as I showed this here on the queue description, to another entity. So you specify here the name of the topic, or here I have two queues, where I have a queue, a destination queue, and a source queue. The source queue, now I set the forward to that destination queue. Create both of them, the destination first and then the source. And with then I have now a queue that automatically forwards to another queue. So we'll do the same thing here for a topic. I create the topic with 3 subscriptions, each have forward to rules, all sent into the next level topic, which then has another set of subscriptions with another set of topics. What this will do is we'll create a tree. And what I said in the beginning is that the throughput of a topic is kind of limited by how many messages it can process in total. So you have the number of messages you can get through this divided by the number of subscriptions. So you're reducing your flow rate. So if you can make this 3 or 5, but you can go and use auto forwarding to go and effectively create a tree out of those, you can keep the flow rate high while scaling to very many by just adding more topics, adding more of these message entities you can flow, so you can actually scale up effectively limitlessly. What we're going to do eventually in the service is we're going to go and abstract this. So if you create a topic, we're going to create these kinds of fan out trees automatically for you. For the time being, you have to go and create them yourself. This is also nice for abstraction of locations. So for instance, you can go and reconfigure a flow very flexibly. You give a sender the name of a particular queue. So let's go and make this queue, or make it the source queue here. So you configure a sender, wherever that subsystem is, and you configure it with a particular queue. You can now in the service go and repoint that queue to a different entity. You can go and point it to this topic, or you can point it to this queue. So you can go and do effectively virtualize the destinations in your system by using the auto forward feature. You can go and reconfigure flows on the fly without even touching the configuration of your individual systems. So that's a very, very powerful feature. If you go and combine these features with the rules and the actions that you have in the topic subscriptions, where you can set new properties based on incoming properties, where you can go and execute those rules, you can actually make very, very powerful flows purely just in Service Bus, dealing with those messages and redirecting and routing flows. So that's a core feature that takes Service Bus from effectively just being a host of queues and topics to something that is actually something that governs the flow and routes the flow of your messages. Currently within a single namespace, but we're also going to extend that feature to be able to span namespaces. So general messaging guidance. I have 2 points really that I want to talk about in the general guidance and things that you should and should not do. The first thing is to be prepared for things going wrong. Customers must be prepared, you must be prepared for things going wrong and operations failing occasionally. All your code needs to be resilient against failures. Yes, you will get timeouts. So it is the code I had earlier with a receive that gets a message and then calling something on the message. No, you can't do that. You have to check the message whether it's null, because we might time out on you. That's an expected thing. If you set a timeout, that will happen. Each operation needs to be guarded by a try-catch block, and you need to look at the messaging exception that we give you. If that is transient, if its transient is true, retry that operation. If you can, do a bit of a back off. So give us 5 seconds, 10 seconds time to recover. All those systems that you're interacting with, even if you're hosting them yourself, Service Bus for Windows Server, are very complex distributed systems, specifically if you have failover configured. So if you're losing a SQL server, or if you're losing one of the messaging servers, you want the system to be up all the time, but the system needs to have time to recover from losing a machine. So that might take several seconds. It also takes several seconds in the cloud. So if you have a receive operation that's nailed up against a node and we're losing that node, we will fail out your receive operation. That means you can come back to us and talk to a different node, which will then happily service it, but we will go and do that. If we do an upgrade, a scheduled upgrade, we do our upgrades without any downtime. We actually don't even announce them because we can maintain our SLA through upgrades. However, we will shoot individual machines. So if you run against them, you will see that individual operations fail, and then you need to be prepared to retry those operations. So every send and also every receive loop needs to be able to retry and needs to be resilient against failure. In our internal testing, it's acceptable if 1 out of 1,000 operations fail. We strive to go much, much better than this. Obviously, we are looking to actually hit 99.99%, and we're actually getting higher than that in particular cases. But it's okay. It's generally seen as okay if 1 out of 1,000 operations fail, because that's in the nature of the beast, because it's a distributed system, because making everything succeed is just difficult and enormously hard. And also kind of getting to 100% is completely impossible, really, in a large distributed system as you run it, if you run Service Bus Server, or as we run it at even higher scale in the cloud. So you need to be, that's a bar that you need to be accepting, kind of, especially if you're calling us from afar. If you have an issue with Service Bus, you can raise a service request through the Windows Azure portal that actually has a support tab. You can go and file that service request against us. That must include the Service Bus namespace name, and your tracing must be so good that you can actually show the text of every individual exception that we throw at you, because that will contain a field called tracking ID. That's a GUID that we throw back at you, and that GUID is actually individually traceable to the logs we have on the back end. So if something goes wrong and repeatedly wrong, we at least need one of those tracking IDs so we can go and identify that. So we need to have the namespace name and the tracking ID, and then we're going to be happy to go and look this up for you if there's a problem that persists over more than, let's say, 5 minutes. Another piece of advice I want to give is that to make everything asynchronous, so begin receive, end receive, begin send, end send, or use the task.factory from async wrappers to kind of make yourself async methods. As I said, later in the year, in a few months, we're going to have a complete set of async overloads for all of our methods. And but one thing to be aware of is don't call begin 500 times to send a lot of messages. Be mindful that these operations are queued up in a job queue. So if you are calling begin 500 times, those 500 begin calls now end up in the thread pool queue and are going to be worked on in sequence, because ultimately you're sending through a serial socket. So don't do that, but use begin send, send, end send. Once end send unblocks, once the operation is done, once the callback gets called, then send the next message out of your process. Don't overload the asynchronous job queue. I'm mentioning this because that's an error that I've seen multiple times in servicing. So we're generally recommending sending and receiving everything async. Stay on the I/O thread pool, because this is an I/O intensive network, I/O intensive operation interaction that we do with Service Bus. But don't make that mistake of mistaking the thread pool queue for the queue that we have in the cloud. And with that, I'm done. That was the overview, fairly lengthy, over the capabilities that we have in Service Bus on messaging. If you have any further questions, don't hesitate to tweet me. And the contact information is right here. So don't hesitate to tweet me at ClemensV, or even if you have something that's more involved, you can also send me an email to my Microsoft address, and I will be happily taking a look at that. And otherwise, happy hacking.